Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Physical layer problems remain one of the most common causes of network issues. Despite how easy they are to check, they are just as easy to overlook. Cables and connectors are handled frequently during installation, maintenance, and even daily office activities. Over time, they wear down, get pinched, are routed improperly, or simply miswired from the start. What seems like a network failure or complex configuration problem often turns out to be a broken pin, a damaged patch cord, or a connector that never clicked fully into place. These faults lead to slow speeds, intermittent connectivity, or complete loss of service, and they frequently masquerade as software or higher layer problems. This episode focuses on physical layer failures related to cables, connectors, ports, and related hardware. You'll learn to identify typical symptoms of cable issues, how to test for them using common tools, and how to determine whether to repair, replace, or reroute a cable. These problems show up not only in everyday IT work, but also frequently appear on the Network Plus exam. By understanding the most common cable faults and how to detect them quickly, you'll improve both your troubleshooting speed and your ability to diagnose Layer 1 issues with confidence. Open circuits and short circuits are two of the most basic but critical wiring problems. An open circuit occurs when a wire is broken or disconnected, meaning that no electrical signal can travel down the wire. This results in a total loss of connectivity or dropped packets. On the other hand, a short circuit happens when two connectors that shouldn't be connected come into contact, such as when exposed wires touch each other inside a damaged cable. Shorts often produce CRC errors and may cause ports to disable themselves or go into erratic states. Both of these problems can be detected with continuity tests or time domain reflectometers. Crossed wires and miswiring occur when the pinouts on either end of a twisted pair cable don't match. This is common in hand-terminated cables or during rushed installations. If the wires are in the wrong order, devices may fail to negotiate a link or may fall back to lower speeds. In some cases, miswired cables still allow a connection, but the performance is inconsistent or errors are logged on the switch port. TIA/EIA standards specify exact pinout sequences for straight-through and crossover cables, and even small deviations can have a large impact on reliability. Split pairs are a less obvious but equally damaging form of miswiring. With split pairs, the individual wires in a twisted pair cable are correct at the ends, but they're not twisted with their intended partners. For example, wire 1 might be paired with wire 3 instead of wire 2. The result is poor crosstalk resistance and a severe reduction in electromagnetic shielding. This causes strange, hard-to-pinpoint problems like slow transfer rates, dropped packets, and increased latency. Unlike crossed wires, which can be caught visually, split pairs usually require a cable certifier or tester that can detect wiring sequence integrity. Intermittent cable failures are especially frustrating to troubleshoot because they don't present consistent symptoms. These issues are usually caused by cables that have been kinked, crimped too tightly, or subjected to excessive bending. As the cable is moved or as temperature or humidity fluctuates, signal quality may change. Users might report, sometimes it works, sometimes it doesn't, and tests run during stable periods may show no problem. Moving the cable slightly during testing may reproduce the fault. These issues are typically resolved by replacing the affected segment entirely. Bad crimps and improperly seated connectors are another source of packet loss and unreliable links. When a connector's metal pins fail to make firm contact with the conductors inside a cable, the signal may be incomplete or noisy. Crimping tools must be calibrated, and cables should be trimmed to the correct length before termination. Visual inspection often reveals uneven crimps, bent pins, or loose cable jackets. These problems can prevent a device from establishing a link or cause the link to flap unpredictably under load. Physical damage to cable jackets and internal conductors is common during or after installation. Cables may be pinched by furniture, cut during construction, or degraded by environmental exposure. Even small tears in the outer jacket allow moisture to corrode internal wires, especially in outdoor or industrial settings. Crushed cables may show no external damage but can have flattened pairs inside that degrade performance. Once structural integrity is compromised, replacing the entire cable is the best option. Splicing or patching damaged network cables is rarely reliable or standards compliant. Patch panels can also introduce connectivity issues, particularly when individual ports become damaged. Frequent plug-in cycles, poor punchdowns, or over-tightened cable bends behind the panel can lead to loose contacts or worn-out jacks. If a user reports intermittent link drops, try moving the patch cable to a different port on the panel. If the issue resolves, the original port is likely faulty. In structured cabling environments, patch panel faults may go unnoticed because the cable run appears intact and the switch port logs no obvious errors, until the port is tested under sustained traffic load. Loose or unseated connections remain one of the most common causes of mysterious link issues. Sometimes a plug isn't fully clicked into place. Other times, dust, corrosion, or oxidized contacts inside the jack prevent a clean connection. These faults cause links to flap, dropping in and out rapidly, or lead to unexplained frame drops, especially during high-speed transfers. Reseating both ends of the cable, using contact cleaner if necessary, and confirming a firm mechanical connection often resolves the problem. Visually inspecting the plastic tab on RJ45 connectors helps identify plugs that fail to lock correctly. Many of these faults can be detected using basic diagnostic tools. Simple cable testers check for continuity and correct pinout. Loopback plugs verify port operation by sending and receiving signals on the same device. Even without advanced tools, visual inspection and movement testing go a long way. Wiggling a cable while watching the interface status lights can reveal intermittent faults that wouldn't be caught otherwise. These tools and techniques are inexpensive, accessible, and effective, making them essential components of any troubleshooting toolkit. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. When diagnosing cable faults, one of the first visual clues technicians look for is the LED indicator on the network interface card or switch port. These LEDs provide an immediate view into the status of the physical link. No light at all generally means there's no physical connection, either due to a disconnected cable, a failed transceiver, or a completely broken line. A solid amber light often signals a negotiation issue, such as a duplex mismatch or speed fallback. A blinking green or amber light may indicate normal traffic, but fast or irregular blinking could suggest excessive collisions or retries. Each device manufacturer may use slightly different LED behavior, so checking documentation is always advised. Still, these status lights are a quick, reliable first step when a user reports connectivity problems. More advanced diagnostic tools include time domain reflectometers and cable certifiers. A time domain reflectometer, or TDR, sends a pulse down the cable and measures reflections to identify breaks, shorts, or impedance mismatches. It can even tell you how far down the cable the problem is located. This is particularly useful for long cable runs where the fault isn't visually accessible. Cable certifiers go further by verifying that a cable meets the performance specifications of its rated category. They test for attenuation, near-end crosstalk, pair alignment, and other metrics, ensuring compliance with industry standards. These tools are essential for new installations and help validate that performance degradation isn't caused by underspec components. Electromagnetic interference, or EMI, is another frequent cause of cable-based issues. Interference can be introduced from nearby power cables, industrial equipment, or even poorly shielded fluorescent lighting. If cables are routed too close to these sources, especially if they're unshielded twisted pair, the signal may degrade or fail entirely. Shielded cables, proper grounding, and maintaining separation between power and data lines are all methods for preventing this. If interference is suspected, rerouting cables using better shielding or replacing with fiber immune to EMI may be necessary. Identifying interference usually involves checking the environment as much as the hardware. Not all faults come from the cables themselves. Faulty transceivers or network interface cards can mimic cable problems. A transceiver might partially function, establishing a link but introducing CRC errors, frame drops, or flapping under load. The same applies to network interface cards with failing chipsets or outdated drivers. Swapping the suspected hardware with a known good component is the fastest way to isolate the issue. If the problem moves with the cable, it's the cable. If it stays with the port or system, suspect the NIC or transceiver. Always ensure firmware and drivers are updated as part of this diagnostic process, especially after OS patches or hardware changes. Sometimes cables are perfectly fine, but the wall jack or faceplate they're plugged into is the real problem. Over time, the retention clips inside a wall jack can lose their tension, causing the cable to wiggle loose or sit in the port without full contact. Dust, corrosion, or physical damage, like cracked plastic or a partially detached faceplate, can also cause connection instability. If replacing the patch cable doesn't resolve the issue, try testing another known good port or use a punch-down tool to reseat the cable in the keystone jack. Always relabel and retest after replacing a wall jack to ensure the change is logged and documented. Environmental conditions play a subtle but significant role in cable and hardware reliability. Excessive heat can weaken cable insulation and increase resistance. Moisture can corrode exposed metal contacts or penetrate minor cuts in the cable jacket. Vibrations from nearby machinery can loosen connectors or break fragile solder joints over time. These factors are especially common in warehouses, factories, or areas with poor HVAC control. For long-term reliability, cables should be enclosed in raceways, trays, or conduit and placed away from sources of physical stress or environmental extremes. Periodic inspections of exposed cabling help catch small issues before they become major outages. Understanding how these issues appear on the Network Plus exam is just as important as recognizing them in practice. You'll often see scenarios where users report slow speeds, dropped VoIP calls, or failed connections, and be asked to identify the most likely physical cause. You might need to determine whether the issue is an open circuit, a bent pin, or an interference problem based on a short description. Some questions may reference the output of a cable tester or ask which tool to use next. Others may ask when it's appropriate to replace a cable versus reseating a connector. Knowing the signs and matching them to layer 1 problems is a frequent theme in troubleshooting questions. To troubleshoot cable faults effectively, always start simple. Check the link lights. Inspect both ends of the cable. Try a known good port or known good cable. Use basic testers before reaching for expensive diagnostics. Document what you find and keep a record of replaced or re-terminated lines. Many recurring problems such as random link drops, inconsistent speeds, or hard-to-reproduce network issues are resolved by replacing a single faulty cable or cleaning up a dirty jack. Layer 1 may not be glamorous, but it is the foundation of the network. Ignoring it adds unnecessary complexity to every higher layer investigation. Let's review the core cable faults discussed: open circuits, short circuits, crossed wires, split pairs, bad crimps, damaged jackets, broken patch panel ports, loose connectors, EMI, failing transceivers, and wall jack failures. Each of these can cause specific patterns of behavior that a trained eye will learn to recognize. Many of them can be solved quickly once identified, others require replacement or rerouting. But all of them are within your ability to diagnose with patience, process, and the right tools. In the end, many of the problems technicians are called to fix start and end with cabling. It's easy to assume a firewall rule, a DHCP failure, or a VLAN issue, when the real culprit is a damaged patch cord or an unplugged jack. Effective troubleshooting begins at the bottom of the OSI model. Layer 1 issues are common, easily testable, and often preventable. By starting with the physical layer, you eliminate guesswork and avoid the trap of overcomplicating the problem. This approach not only makes you a better troubleshooter, it saves time, builds trust, and resolves user issues more efficiently. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.